no final do evento, mas, sem dúvida alguma, eu não tenho como deixar de iniciar o nosso 15º simpósio sem agradecer a comissão organizadora. Temos um pessoal do Fiocruz envolvido na transmissão. Eu vou falar melhor sobre as meninas ao final do evento. Os palestrantes que gentilmente aceitaram participar desse evento online, dispensar alguns minutos de suas intrincadas agendas, poder conversar conosco. E antes de seguirmos nas palestras e iniciarmos oficialmente o evento, eu gostaria de pedir a todos que tomassem conta dos seus microfones, câmeras. Vamos mantê-los fechados, embora nós possamos fazer o controle, mas seria bom que as próprias pessoas fizessem isso. Então, câmeras fechadas, microfones desligados durante as apresentações. Nós procederemos às perguntas ao final das palestras, em havendo tempo, obviamente, pedindo que vocês coloquem no chat essas perguntas. E uma coisa importante para aqueles que entraram aqui na sala e não tiveram a oportunidade de renomear, colocar seus nomes adequadamente, por favor, façam isso, tá? Nome e sobrenome. É importante para que nós possamos fazer um controle adequado da presença de vocês e seguimos no evento da melhor forma possível, ok? Então, teremos 3 dias de programação. Eu vou projetar rapidamente, só para fazer uma rápida recapitulação do que teremos. O evento vai ser transmitido pela plataforma Zoom, então os links estão disponibilizados para aqueles que eventualmente esquecerem dentro da programação. Então, aqui na programação, no nosso site, vocês vão encontrar os links, caso esqueçam, ok? Teremos 2 dias inteiros de programação, hoje e amanhã, incluindo aí a plataforma de apresentação de vídeos, ao final, meio da tarde, e amanhã e quarta-feira, no horário da manhã, no último dia de evento. Então, para que possamos começar pontualmente nosso evento, eu gostaria de convidar, então, o Dr. Martim Bonamino, que foi a pessoa que convidou nossos próximos palestrantes. E antes de sair, eu vou só dar as boas-vindas para o nosso palestrante, que é o nosso primeiro speaker. So, Dr. Antonio, thank you so much for joining us for the event. And Martim, você, por gentileza, faz a apresentação. Vou sair aqui do compartilhamento de tela e sigamos, então. Eu gostaria, então, de dar as boas-vindas a todos e que a gente tenha um 15º simpósio bastante proveitoso para todos. Muito bem.
Robson, muito obrigado. Então, bom dia a todos, bem-vindos. Buongiorno, Antonio. So, Antonio is our first invited speaker. He's a good friend from old times in Italy. Antonio is currently Associate Professor of General Pathology at the University of Study Piemonte Orientale. And he received his PhD in immunology with training at the NCI. And then he, for many years, had the Laboratory of Molecular Immunology at the Mario Negri Institute, where we met a long time ago, while I was there during my PhD. And he later moved to the Humanitas Institute, still in Milan. Dr. Sica is also the professor at the University degli Studi Piemonte Orientale, as I already said, where he coordinates the Laboratory of Pathology and Immunology. His research is mainly focused on the study of cancer and inflammation, with particular interest in the role of myeloid cells. Ever since I know Antonio, he has been working with those myeloid cells, making very important contributions to different phenotypes and roles of those cells in different processes, not only cancer. But today, since we are in the oncobiology meeting, he will be speaking about the role of those cells in tumors, right? So Antonio, thank you very much for joining us today here, for taking some time to share with us. And it's all the stage, and I'll be in background and take. So please, any of us who want to make any question, you can write it in the chat, and I will bring them to Antonio as soon as we finish his presentation. Okay, Antonio, thank you very much once again. You're in mute, and Antonio, have to open the. Okay. Great.
Yes, I was saying that I'm trying to share my screen, and let me know if it's okay, if you can see properly the video.
We're seeing not in presentation.
No, is loading now. No,
okay.
Yes, but just 1 second.
Yes, you're sharing this one.
Fantastic. How is it?
Perfect.
Can you see? It's fine.
Yeah, it's perfect.
Wait a second, because I can't control. I have two videos. How is it now? Sorry.
It's all black, the screen, but I can see your point, so should be okay.
Wait a second, just sorry, because now
still black.
Black.
Yeah, all dark screen, but I can see your pointer moving. So
strange.
It's something with the video. Not...
Zoom share. Okay, I'm trying again.
Okay. So yeah, I can see your first slide.
Okay. You see the slides then? Now it's fine?
I see the second slide now. Myelopoiesis.
Okay, perfect. So no, I want to thank very much really Martin and Robson for organizing this meeting, giving me the opportunity to present our science to you. Actually, is a real pleasure to share with you, with your country, your people on the other side of the ocean, our science. I know Martin since a long time, as he mentioned before. He was in Milan, and both we work in the Department of Immunology. And actually, it's been a long time, and I'm not associate professor, actually, Martin. Now I'm a full professor. You know, this is a sign that time is rolling on.
Fantastic.
So in addition to accept the invitation with a great pleasure, of course, I would like to say yes to another proposal of Martin. He proposed to play soccer. And so I will look forward to play soccer with you once the pandemic will allow us to stay together. So besides this, okay, I will talk about cancer inflammation, basically, the role of innate immunity in cancer inflammation, and how the repertoire of innate immune cells are controlled by different mechanisms. And I would like to point much of the attention on myelopoiesis. Myelopoiesis, of course, is the first event which contribute to the generation of different immune cells, basically all the immune cells, including myeloid cells. Generation of myeloid cells starts from hematopoietic stem cells, then common myeloid progenitors, which differentiate to the different subset that we know quite well. Again, this is a simple scheme that we teach to our students, and is the physiological myelopoiesis, however. We have to keep in mind that in cancer, as well as infection, in immunological stress condition, basically, we have alteration of this hematopoietic output, and we encounter in the periphery, in the blood, for example, a number of new coming myeloid population with different phenotypes. For example, there is an expansion, as we know, of immature myeloid cells. So are basically myeloid cells which do not complete their terminal maturation. And within this class of cells, we find a number of suppressor myeloid cells which expand during cancer progression. So again, this process, the activation of high output of myelopoiesis is defined as emergency myelopoiesis, is meant to provide an increase in the level of defense. Of course, we need more, for example, cells, immune cells, to defend ourselves against infection, against cancer. But the result is that, again, we generate a number of immature myeloid cells which can contribute in general to immune suppression. And then these cells, of course, are recruited from the circulation to the tumor site into the lesion by different chemotactic mechanisms. And they encounter, again, other very extreme conditions, which are due to the different microphysiology of the tumor. For example, we have a low glucose level, low oxygen levels, low pH. So all these extreme conditions, they will again impact the condition, the phenotype of these cells. So this gives you an idea that the final phenotype of tumor promoting myeloid cells is also depending on different steps, different level of mechanistic level that can somehow contribute to the final protumoral phenotype of these cells. Again, there is an extreme heterogeneity in the myeloid compartment. If we talk about macrophage, which is the main topic in my presentation today, we learned that there are basically three different routes for the generation of these cells. We have the so-called tissue-resident macrophage, which are generated from the Yolk sac. You know this notion, of course, but I like to refresh this concept, which provides the so-called tissue-resident macrophages. And this pathway is mainly controlled by this growth factor, which is the colon-stimulating factor 1 and IL-34. Again, in the fetal, during the fetal life, the liver can contribute to the generation of the so-called Langerhans cells through a similar mechanism. Again, CSF1 is still very important, and the generation of Langerhans cells is considered to stem again from a progenitor, which are generated during the Yolk sac period. Finally, we have the adult life, in which the majority of myeloid cells are generated from the bone marrow progenitors, of course, and these progenitors gives rise to monocytes, of course, circulating monocytes, which can differentiate in two different subsets, LY60 low or negative or positive. And then a positive one are defined as inflammatory monocyte, basically, and can also be recruited to the tissue, and somehow in different tissue can replace the tissue-resident macrophages. You can see that there is a lot of heterogeneity, of course, and this again is based also on the type of ontology that the different subsets meet. Again, another level is the tissue microenvironment. It's not only the pathological tissue such as cancer, but a different tissue, brain, lungs, spleen, and so on. Of course, they deliver other type of signals. For example, in the lungs, we have the GM-CSF actually, which activate the PPR gamma, which promotes a specific transcriptional program for alveolar macrophages. So there is an additional specialization of macrophage function in response to the tissue microenvironment. It is in physiology, actually. Again, and then we met another level again, which is is based on the plasticity of these cells. Macrophages, as you know, are able to express different functional programs. The two extremes are defined as M1 and M2. Basically, M1 are representing the classical inflammatory macrophages, and this program, transcriptional program, is activated in response to classical inflammatory signals such as bacterial products, inflammatory cytokine, and so on. And these cells are endowed with cytotoxic activity, antibacterial function, and can activate Th1-mediated immune responses. You can see that in this quite old review, actually, we review actually the state of polarization in vivo of macrophages. And you can see that M1 polarization or activation states is associated with a number of pathologies. For example, viral infection can induce M1 activation. Hypersensitivity type 3 lupus erythematosus, which is an autoimmune disease, also activates the M1 response. Steatosis, liver steatosis, arthritis, atherosclerosis. Atherosclerosis is a chronic inflammatory condition which is associated with M1 inflammation, and also diabetes, at least type 1 and also type 2 diabetes actually is associated with M1 polarization. On the other side, we have the M2 or alternative macrophages, which develop an anti-inflammatory, immunosuppressive, and pro-angiogenic phenotype in response, for example, to Th2 cytokines, IL-4, for example, or IL-10 also. And in this case, these cells have a role actually in other type of diseases. Of course, breast cancer, as you know, most of the cancer have been described as to be populated by preferentially skew macrophages skew toward the M2 polarization states, but also in a parasite infection, helminths, granuloma formation, fibrosis is sustained by this type of polarization. Again, wound healing and asthma, for example, which is of course linked often to hypersensitivity type 1. So it's very important this concept, because as I suggested that probably by learning how to pilot the polarization of these cells, we can interfere with the onset or progression of different type of diseases. So the point is to understand the role of the polarization in vivo, and to understand, to identify mechanisms to revert, to reprogram, to re-educate these cells in vivo. So let's go to cancer. What we know is that the infiltration of tumors by macrophages actually is a sign of bad prognosis. In other words, extensive time infiltration correlates with poor prognosis in different variety of cancer, both in preclinical models as well as in a clinical, in a human patients. And here there are a number of evidences. Again, how do they contribute to the progression? Of course, has been an object of a long study. We know that these cells again are immunosuppressive. They promote angiogenesis. They are again they provide remodeling of the matrix, extracellular matrix, so they contribute to the metastatic formation. And they also express a number of immune checkpoint molecules, immune checkpoint inhibitors, which of course are very relevant for, can interfere with the efficacy of immunotherapy, as we know. And there are a number of other mechanisms that can be targeted. In this slide, for example, is shown aspirin. Aspirin is, of course, as inhibitor of cyclic oxygenase, and the activation of cyclic oxygenase has been linked to a number of protruminal functions, which I will recall later in my presentation. Again, we can interfere with chemotaxic agents. For example, tumor-associated macrophages are recruited in the tumor lesion by different chemokines. For example, CCL2 is one of the first identified. Complement factor can promote, enhance the infiltration of tumor-associated macrophages. And again, survival signal. For example, again, MCSF1, macrophage colony stimulating factor, which binds its receptor. Also, VEGF receptor can provide survival and recruiting signal to these macrophages. Then trabectedin is one recently identified chemotherapeutic agent, which in vivo provides depletion. It's a cytotoxic, can induce apoptosis of tumor-associated macrophages. So depletion is also another alternative way to limit the tumor-promoting function of these cells. So all this scenario has led to the several efforts that, again, as I mentioned, to re-educate the function of these cells, and also to the concept of targeting the tumor microenvironment. So targeting the tumor microenvironment, of course, is a very good, is a sort of a mirage, a sort of goal that many groups are trying to reach. because the tumor microenvironment, of course, is composed by cancer cells, immune cells, stromal cells, and is very relevant because it can be the site of tumor promoting permissive condition for tumor growth, expansion, and metastatic formation. These are the bottom side of the slides actually refer to a recent review written by Bruni and Jeremy Gallon. You know, Jeremy Gallon has conceived the concept of immunoscore. Basically, he estimated the type and frequency of infiltrating immune cells in different type of tumors, and the scenario, the final scenario is that in several tumors, as we know, macrophages, and mainly M2-polarized, are indeed associated with bad prognosis. Of course, in this review, which is quite nice, actually, he considered other type of cells, for example, T cells, B cells, and so on. So it's a very good review. So this scenario, again, has a prompt another effort, the effort to deliver immunotherapy within the tumor, so intratumoral delivery of anti-cancer or anti-cancer agents. And this has one big advantage, actually, because, of course, often anti-cancer therapies are quite toxic, and the possibility to deliver anti-tumor activity within the lesion, of course, can limit the toxicity. It can improve probably the efficacy of anti-tumor activity. However, there is a very clear and obvious limit to this approach. Several tumors are not focal lesions. They are a multifocal lesion. They are multicentric in different regions of one organ, for example. They are multi-lobed or multifocal. And quite often we find patients with advanced cancer stages, so they are metastatic. So it will be quite difficult, quite probably poorly realistic to think that by intratumoral delivery of agents, anti-cancer agents, we can cure cancer patients. So we have another approach to counteract or to generate, if you want, possible anti-cancer strategies, is to target systemically a number of mechanisms which support the generation of a tumor-promoting myelopoiesis. Normally, when a tumor is growing, it promotes, as I say, an increased myelopoietic output, which is defined as emergency myelopoiesis. This is based on the production by tumor of a different tumor-derived factor, but also myeloid growth factors that we can find in the plasma of this patient. We measure this actually. They are improved, so there is a higher production. Colony stimulating factor for myeloid cells, but also for other lymphoid cells, for example, of course, promotes the enhancement in myeloid progenitor differentiation and proliferation, which results in monocytosis, neutrophilia that it can be found during infection, of course, but also in cancer patients. And as I mentioned before, in the expansion of immature myeloid cells, which are mainly protumoral cells, so are the so-called myeloid-derived suppressor cells. This is the first step of this emergency myelopoiesis. Following this increased differentiation proliferation, there is a 1 second key event, which is the mobilization of these cells from the bone marrow to the periphery. So this is not a passive event. This is controlled actively by a number of anchoring molecules. For example, chemokine receptor of adhesion molecules can retain these cells into the bone marrow, and these need to be deactivated in order to allow the mobilization to the periphery. Once in the periphery, of course, cells, myeloid cells, suppressor cells can reach secondary lymphoid organs where they can instate in a immunosuppressive condition, of course, can impair antigen presentation, T-cell activation, lymphocyte activation, and so on. But also they can reach the tumor, of course, through a number of chemotaxis factor. And as I mentioned, they are undergo to a further step of reprogramming due to the extreme microphysiology and cancer-related inflammatory signals that they find into the tumor. So this is a multi-step model. which can offer somehow different level of therapeutic intervention. We can try to interfere with emergency activation of myelopoiesis, mobilization, or the reprogramming of immune cells into the tumor. So even if we can use, what is the limitation of the actual anti-cancer therapy? Let's assume that we can reject the tumor. Quite often, this response is a partial, and we still have a relapse of metastasis, for example, of a cancer disease, which will restart again the emerging myelopoiesis, mobilization, and again the tumor support due to the suppressor function of these cells. So the goal is to abolish these vicious circles by targeting different steps of this network. So first of all, we concentrate on the emerging myelopoiesis, and we look for a marker of a cancer inflammation. What means? Means that we were looking in the bone marrow whether we could find, a marker that is associated with tumor growth and progression. We use this simple model. This is a model of fibrosarcoma, is a preclinical model. We injected this fibrosarcoma cell line in a tumor, 57 black 6 mice, and we isolated the myeloid compartment from blood, from spleen, and tumor, of course, at 2 different stages of tumor development. AD stands for early disease, and the early disease, the mice have small tumors, small number of metastases, and then to advanced disease, in which they have high, big tumors and high number of metastases. When we look in the blood, but also in the spleen, here for sake of time, I show only part of the data, of course. You can see that in the early disease, we did not find this subset of myeloid cells. This subset is characterized by expressing high level of this transcriptional factor. Transcriptional factor is a ROR1, named also ROR gamma, is a member, is a nuclear or the nuclear orphan receptor, which is activated in response to cancer-derived signals. You can see that the blood is present only in this condition, in advanced stages. The cells, mainly, these are myeloid-derived suppressor cells, monocytic, granulocytic cells, which express ROR1 in their nucleus. So these are markers of advanced cancer inflammation. Again, the same can be observed in patients. These are colorectal cancer patients, stage 2 and 3. You can see that this population, ROR1 positive, monocytic, MDSC, and granulocytic, are observed only in cancer patients. Again, what is inducing the presence of ROR1 in these cells, which is associated with, of course, with monocytosis and emerging myelopoiesis in these patients? We screened the level of different myeloid growth factors, and as I mentioned before, we found that all the major myeloid growth factor, granulocyte colony stimulating factor, granulocyte macrophages, macrophage colony stimulating factor, are increased during tumor progression, during tumor growth. Again, when we treat the cells, this was a pilot study, myeloid cells with this factor in vitro, and we look for the activation, induction of ROR1, we observed that all these myeloid growth factors were able to induce ROR1 expression in the myeloid cells. So probably this population, which is expanded during cancer inflammation, is controlled by a direct activation of ROR1, which is through the myeloid growth factor. So what is the functional significance of this event? Well, of course, we use knockout mice and then myeloid-specific knockout mice. We grow the tumor again, and we look at the population in the spleen, myeloid-derived suppressor cells in the spleen, which are labeled, recognized by this marker, which is the IL-4 receptor, has been described to be a specific marker of suppressor myeloid cells in mice, in the spleen mainly. And you can see that when the tumor grows in wild-type mice, the spleen is a site of accumulation of myeloid-derived suppressor cells, but in the absence of ROR1, basically we do not have expansion of this population. This is the spleen. Same situation in the tumor. In the absence of ROC1, we have a drastic decrease of monocytic MDSC and granulocytic MDSC. So basically, ROC1 expression is very important to lead expansion of myeloid-derived suppressor cells, so immature myeloid cells, which are known to promote, support cancer growth and progression. I will not go in detail, but basically what ROC1 does is to block the differentiation of from colony common myeloid precursor to granulocyte macrophage precursor. So is a sort of inhibitor. When you have a lot of ROC1, basically you do not allow the terminal maturation of the progenitors in this direction. So what is the relevance for the tumor growth? This is an experiment in which we transplanted ROC1 deficient bone marrow cells in lethally irradiated wild-type mice. So basically these mice are ROC1 knockout only in the hematopoietic systems. And you can see this in this model of spontaneous mammary carcinoma that in the absence of ROC1 in the myeloid compartment, in the hematopoietic compartment, basically you have a strong impairment of tumor development. These are mammary carcinoma, similar result obtained with a fibrosarcoma. This is the primary tumor, but you can see there is a very important reduction in terms of number of metastases when we remove ROC1 from the hematopoietic compartment. And this inhibition is dependent on T cell activation, because when we removed the CD4, CD8 T cell subset with specific antibodies, you will restore the high number of metastases. So basically targeting ROC1 in the hematopoietic compartment, I will show you in the myeloid compartment specifically, is able to reactivate specific anti-tumor immunity. So this is basically the scenario, the information that we got from this paper. Basically, ROC1 is induced by cancer inflammation, a number of myeloid growth factors, but also inflammatory cytokine. I didn't show this. And basically, this results in the expansion of immature tumor-promoting cells. These are monocytic and granulocytic MDSC, which, of course, produce high level of suppressor molecules, such as nitric oxide, reactive oxygen species, which impair CD4 and CD8 activity. Again, I didn't show, but ROC1 also promotes skewing of macrophages toward an M2 alternative tumor-promoting phenotype. Blocking ROC1, of course, blocks all these events, tumor-promoting events, and reestablish terminal maturation of monomacrophage neutrophils, which are also very good cytotoxin, but also antigen-presenting cells. And then we have reactivation of specific anti-tumor immunity. So this is a first evidence that targeting the progenitor myeloid cells or event which controls the quality and the level of myelopoiesis can interfere with tumor growth. So because the myeloid growth factors are inducing ROC1, of course, we tested the ability, the anti-tumor activity of myeloid growth factor antagonist in vivo. And indeed, when we block either GCSF, GM, or GSFR receptor, we do see a very relevant inhibition of tumor growth. This is a primary tumor, again, this is the fibrosarcoma model, and also metastasis formation. You see that the most important effect was provided by an antibody which blocks the CSF receptor 1 receptor, which is, of course, the receptor for macrophage colony stimulating factor. This is relevant also because this antibody is now in clinic actually, and we co-authored this paper back in 2014, and you can see that this young patient, this is a 19-year-old patient carrying this type of tumor, which is named pigmented venulonodular synovitis, is being treated with two different injections, single injection, in 2 different weeks, actually. You can see that the anti-MCSF receptor antibody has provided a drastic reduction, disaggregation of the tumor mass. So blocking MCSF activity in vivo provides an anti-tumor activity. Now, this antibody is in the clinic. There are a number of clinical studies ongoing, not very successful, actually, but somehow is considered as a monotherapy. New evidence now are suggesting that its combination with immunotherapy, for example, with immune checkpoint inhibitors, pembrolizumab, and so on, can provide, can enhance actually significantly the activity of this immunotherapeutic approach. I go on, but you can stop me at any time, of course. Martin, you can stop me, you can tell me. Okay, this was the first level of study that we wanted to go in deeper. Now, actually, we are studying more in detail this event, this step, this level of control of myelopoiesis, and we are studying this in relation to the metabolism, host metabolism, actually. Okay, but following the activation of emerging myelopoiesis, as I say, you have the necessity to mobilize the cells into the periphery. So the myeloid cells, which are produced, they have to leave the bone marrow, enter the circulation, so that they can act as immune cells, but they can also infiltrate, in this case, of course, the tumor, providing tumor-promoting activities. So how is controlled the mobilization of myeloid cells? This is a simple model that gives us some insight. Basically, when we challenge the bone marrow progenitors with myeloid growth factors, what we end up is a high proliferation of these cells. Basically, they undergo to proliferation, of course, and this is paralleled by high consumption of oxygen. There is a high oxygen consumption, and this results in a local hypoxia. So the bone marrow becomes hypoxic, basically. And hypoxia, as you know, is the strongest activator of this transcription factor, the so-called hypoxia-inducible factor 1 alpha. And what does this molecule, this transcriptional factor, basically is to induce, of course, hypoxia-inducible factor genes, such as CXCR4. CXCR4 is a chemokine receptor, chemotaxis receptor, which bind CXCL12, actually, but is also acting as a retention gate. So is one of the main anchoring molecules which retains myeloid progenitors into the bone marrow. So if you have high expression of CXCR4, the myeloid cells do not leave the bone marrow. They do not go to the periphery. And actually, you know that antagonists of CXCR4, such as AMD 3100 or GCSF itself, is used in patients, cancer patients, which undergo to leukopenia, neutropenia, for example, in order to improve the release, the exit of the cell to the periphery. So in order to establish a normal leukocyte count into the periphery. So CXCR4 is an anchoring gate, okay, which is induced by hypoxia, local hypoxia. What we found out is that MCSF, which promotes myeloid differentiations, is actually an inhibitor of this molecule, these anchoring molecules. You can see that by blocking MCSF in this experiment, for example, we enhance the level expression of CXCR4 in a monocytic and granulocytic MDSC. So this is antagonizing the receptor. We block its action, and we increase the level. So this tells you that MCSF is, of course, able to decrease the level of CXCR4, both at the level of percentage of CXCR4 positive cells, but also as a mean flourishing intensity. We do see this. So what I mentioned you is that MCSF induces high proliferation, promotes hypoxia, activates IF1 alpha, and promotes CXCR4, which of course is a retention gate again, as I mentioned. So we reason that there is a natural antagonist of IF1 alpha, which is this molecule, is a deacetylase, SIRT1 alpha, which is a NAD-dependent enzyme. And the NAD accumulation, which is the cofactor for SIRT1, is induced by this enzyme, which is a nicotinamide phosphoribosyl transferase. So we reason that probably this pathway could deacetylate IF1 alpha, so deactivate IF1 alpha, so deactivate CXCR4, and probably promote the mobilization of myeloid cells. Then we look for a connection between myeloid growth factors and this pathway, which is an antagonist of IF1 alpha activity. And this is a very simple experiment, and we simply monitor the distribution of myeloid cells between the bone marrow at the periphery. In mice which have been deleted of NAMPT, nicotinamide phosphorybonyl transferase, only in the myeloid compartment. These are lys M3 knockout mice for NAMPT. You can see that in the bone marrow, when we ablate NAMPT, we have higher frequency of myeloid-derived suppressor cells in the bone marrow. So probably this is an indication that the cells do not leave the bone marrow. When we look at the periphery, actually, we found a specular situation. This is the blood. You can see that in the blood there is a less frequency of MDSC as opposed to the bone marrow, and also in the spleen. So this really suggests to us that NAMPT through SIRT1 alpha could control the localization, the distribution of these cells between central, primary lymphoid organs and the periphery. And this is an immunohistochemistry for the bone marrow and the spleen. You can see it again in the absence of this CRE, the bone marrow has higher level of CXCR4 positive cells. Contrast, spleen, which is the periphery, there's a drop. And when we remove NAMPT from the bone marrow, we have higher infiltration of lymphocytes, both in the intratumorally and peritumorally. So again, mobilization appears to be another level of control for the accumulation of suppressor myeloid cell to periphery. And so by contrasting the mobilization of suppressor myeloid cells, we can somehow reinstate anti-tumor activity. And this is the in vivo evidence. We have again the lys-CRE NAMPT knockout mice. These are the control mice. You can see that the absence of NAMPT in the myeloid compartment results in a strong inhibition of tumor growth, which is basically the same extent of inhibition that is provided by an anti-PD-1 antibody. In combination of two, there is a small additive effect, but which is quite interesting at the level of lung metastasis. You can see that combination of anti-PD-1 with silencing of NAMPT in the bone marrow can result in an increased limitation of lung metastasis formation. So I will make this story short because we reconstructed the entire pathway which connects MCSF to CXCR4. And basically, I already mentioned, by different conditional knockout mice, we were able to demonstrate that MCSF promotes NAMPT activation, nicotinamide phosphorybonyl transferase. This enzyme is the rate-limiting enzyme for NAD production, so its activation produces NAD, which is a cofactor for SIRT1 alpha, which is the acetylase, which inactivates IF1 alpha. So activation of this pathway leads to the silencing of CXCR4, and therefore allows mobilization to periphery. And this is assumed in this small video. We have MCSF, which has, of course, myeloid growth factor action, results in proliferation, consumption of oxygen in the in the bone marrow compartment, activation of IF1 alpha, CXCR4, but in parallel, MCSF act as activator of this cascade, NAMPT, SIRT1 alpha activation, inhibition of IF1 alpha, loss of CXCR4 expression, and mobilization of this cell to the periphery. So basically, these two pathways needs to be combined in order to allow to the proliferating progenitors to get out of the bone marrow and to instate, in case of tumor, of course, immunosuppressive condition. Okay, this already I already shown. So this is the second level. So I show you one part relative to the activation of emerging myelopoiesis in cancer bearers. Now I show you one part which is related to the mobilization of these suppressor myeloid progenitors. And the last part is I will discuss mechanisms which are related to the reprogramming of immune cells within the tumor microenvironment. I already showed you these slides, actually. I already mentioned that the tumor has a very extreme microphysiological condition, which can affect, in addition to other signal, tumor signal, the phenotype of the cells. And this is one of the some paper that we published back in the years, actually. We've been the first group, actually, to generate the transcriptional profile of tumor-associated macrophages back in 2006. These are tumor-associated macrophages from, again, a fibrosarcoma model. And we found out that these cells express mainly an M2-like phenotype. They are characterized. Sorry, something. Okay, they are characterized by M2 signature. And this M2 phenotype is associated with a nuclear accumulation of this transcriptional factor, P50 and FKB. These are peritoneal macrophages, these are control macrophages, and these are tumor-associated macrophages. You can see that P50 is in red, the nuclei are stained in green. In time, there is a strong colocalization of P50 into the nuclei. So basically, these cells are packed, constitutively packed with a nuclear P50. These are, again, a Western blot. You can see that untreated tumor-associated macrophages, there is a high level of P50, nuclear P50, as compared to PEC. The same result is in a human tumor-associated macrophages. These are patients with, in which we studied tumor-associated macrophages from ovarian cancer. You can see that these are control cells. There is no yellow in the nuclei. Tumor-associated macrophages from ovarian cancer patients, both the primary tumor and the metastatic omentum, they are, again, packed with constitutively high level of P50 and FKB. What is the functional significance? Well, P50 actually is a tolerogenic translational factor in the sense that if you expose macrophages to inflammatory signals such as LPS for a long time, at least 24 hours, macrophages do not express any more inflammatory cytokines in LPS, which is an inflammatory signal, but they start to express IL-10, anti-inflammatory cytokines. This is very important because it limits tissue damages, of course. So macrophages have an intrinsic capacity to skew their function from M1 to M2 in response to a chronic activation with inflammatory signals. However, this diversion from M1 to M2 is led by these molecules, P50 and FKB. So if you have high level of an FKB, the macrophage express only M2 programs. That's the point. If you find, for example, if you look, for example, in peripheral blood from septic patients, you will find that these patients often they have high accumulation of P50 and FKB in the nuclei of monocytes. So it's in an attempt to buffer the overwhelming inflammation. So P50 is important to control the polarization, and here is another evidence which support this conclusion. These are macrophages. We studied 3 different pathologies. These are helminth infection. Helminth infection is associated with M2 polarization, actually. And you can see that in wild-type mice, the load of parasites in mice infected in wild-type mice actually is very low. And this has a clear significance because M2 polarization is a protective against helminth infection. However, if we remove P50, which does not allow M2 polarization, you have a strong increase in the parasite load in the peritoneum. So again, we can control the type of polarization, we can provide therapeutic benefit. In allergy is the polarization, which is protective, is M1 Th1. These are alveoli in a model of asthma induced by ovalbumin, aerosol ovalbumin. You can see the wild-type macrophages are stained with the green. These are P50 knockout mice. You can see that there is no P50. Again, when we challenge the mice, the wild-type mice with ovalbumin, we induce asthma. There is a strong infiltration of neutrophils, eosinophils around the alveoli. In the absence of P50, there is not allergic inflammation. So in this case, lack of P50 promotes M1 protective inflammation. Similar for cancer. In cancer, this is a colitis-associated cancer model. These are tumors which are grown in wild-type mice, the black bars, and P50 knockout mice. You can see that in the absence of P50, we have very low number of tumor lesions, also in terms of size and tumor load. And these are the cross-section of wild-type mice. You can see that the lume is completely obliterated by tumor mass, but in the absence of P50, we have a strong protection. If you look at the inflammatory profile, in the absence of P50, you have high upregulation of M1-related genes. So it's a real controller of polarized inflammation. These again are colorectal cancer patients, stage 2 and 3. We monitor, we estimated the level of P50 in a tumor-associated macrophage in the invasive margin of this tumor. You can see the patient with high level of P50 in CD68 positive macrophages, they have a worse prognosis in terms of disease-free survival and disease-specific survival. And the high level of P50, of course, decrease strongly a number of the expression of a number of immunostimulatory cytokines. So basically, is a high level of P50 can tune down immunostimulatory cytokines, which are associated normally with anti-tumor response. So I will spend the last 5-7 minutes on the last piece of data that I wanted to show you. Again, P50, I show you that can modulate the polarization of macrophages, but it can control also the heterogeneity of tumor-associated macrophages. This is a model, again, is our model of fibrosarcoma. You can see that we monitor two different populations within the tumor lesion, actually. These are F480 high macrophage and F480 low. So we then studied these two populations. We found out that in the absence of P50, actually, the high population, F480 high population, is strongly decreased both in the primary tumor and in metastasis. The F480 low population is not clearly affected. Again, similar result for the B16 melanoma models. In absence of P50, we have drastic reduction of F480 high population, no effect on the low population. So P50 is controlling this subset. Similar results have been obtained with by blocking the receptor for MCSF, colon stimulating factor receptor 1. You can see these are the two populations. When we treat the mice with anti-SSF receptor, basically we ablate completely the F480 high population, both in tumor and the metastasis. So there is a clear control of myeloid growth factor MCSF on this population. And you can see that there's another, again, staining of the lung. There is a metastasis, the control after the treatment, we have loss of this cell. And again, we have a strong decrease in the number of vessels, so decrease angiogenesis. And also decrease proliferation of tumor-associated macrophages. You know, macrophages can proliferate in situ in response to MCSF in addition to IL-4. So MCSF seems to control this subpopulation. Then we screen the phenotype of these cells. The high population, the low population, they express similar pattern receptor, but with distinct, very different level of expression. You can see that the 480 high population have higher level of chemotaxis receptor, C5 receptor, angiotensin receptor, MCSF receptor, and chemokine receptor. And these different expression correlate with different capacity to migrate in response to chemotaxis agonist. You can see that these are controlled the white, but just concentrate on the low and high population. There's a better migration, better migration, better migration. So these are two different subsets which are functionally different. We screen the transcriptional asset of this population. You can see that by genome-wide analysis, this population can be very well differentiated. So these are two different populations. These are a pairwise differential analysis in which we identify more than 5,000 differentially expressed genes. And by checking the gene ontology enrichment analysis, we found out that these cells are very different in terms of iron-related genes. So iron is very important for infection, for cancer cells, and so on. So the majority of iron, however, resides in the photoporphyrin ring of heme. Heme is an heme-oxygenase enzyme, of course, which is able to catabolize the heme group. And then we screened the level of expression of heme-oxygenase to see whether the two populations, which are distinct in base of iron-related genes, express different level of heme-oxygenase. You can see that the F480 high population express much higher level of heme-oxygenase 1. And also express higher level of CD163, which is the receptor for the hemoglobin aptoglobin complex, which is we demonstrate that is the first route for heme uptake in these cells. So this is quite relevant because heme is an enzyme, as I say, which metabolizes heme-oxygenase, metabolize heme, giving rise to the production of carbon monocytes, and iron. Iron, as I mentioned, is used by bacteria, by cancer cells to grow, but carbon monocytes, which is quite relevant, has anti-apoptotic, cytoprotective activity, and pro-angiogenic activity. So we generated a conditional knockout for hemooxygenase, and you can see that this is a fibrosarcoma in cane. We have a drastic, this is a myeloid conditional knockout, drastic reduction in the number of metastases. Again, in combination with anti-PD-1, we can ameliorate, we can improve the efficacy of immune checkpoint inhibitors. You can see that anti-PD-1 result in the reduction of the number of metastases. Yeah. And this is paralleled by activation of specific anti-tumor immunity. We have an increased number of effector T cells, which express gynzyme B, interferon gamma, and the ratio between CD8 and T regulatory cells is increased. So we have definitely activation of this pathway. Again, this response is T cell dependent, because when we deplete the CD4 and CD8 cells, we restore metastasis formation. This is another example, again, in combination in the melanoma, combination with an inhibitor of hemooxygenase results in a strong inhibition of tumor formation. I will skip this part. Okay, sorry. Again, one important part is that the anti-tumor activity of hemooxygenase, inhibitor, sorry, is due to the fact that we can interfere with the epithelium-mesenchyma transition. This is again a conditional knockout mice in myeloid compartment. We estimated the expression level of different genes related to AMT. And you can see that in the absence of hemooxygenase in myeloid cells, we have loss of mesenchymal genes, while we improve the expression of genes associated with epithelial condition. So we blocked basically the first event of metastatic formation. These cells are located at the periphery of tumor. These are, again, murine tumors. These are patients, melanoma stage 3 and 4. And you can see that they are located at the periphery, and hemooxygenase is co-localized with CD68, a marker for human macrophages. I will skip this because it's too late. What I want to tell you is that we found the progenitors of these tumor-associated macrophages in the periphery of a melanoma patient, stage 3 and 4. We screened 92 patients. We estimated the level of HO1 expressing monocytes. We identified 15 different subsets of monocytes. Even if I present only the 3 classical, non-classical intermediate cells. And anyhow, when patients express high level of hemooxygenase in the circulating monocytes, they have really poor survival. You can see that the survival is discriminated very well based on the level of expression of HO1 in circulating monocytes. And this again is another evidence in which we screen the significance of hemooxygenase expression and also M2 related genes in the Cancer Genome Atlas melanoma dataset. You can see that again, these are 47.2 patients, 47.1 actually. You can see the most relevant gene is hemooxygenase. So hemooxygenase and myeloid cells, circulating myeloid cells in cancer bears are predictor of survival and peripheral predictor of survival. So it's a blood prognostic marker. So this is the final slides. I want only to underline that, of course, we look for immune checkpoint inhibitors. Immune checkpoint are basically considered to be expressed by T cells now. Everybody is looking at T cells. But what I'm trying to underline is that we have other opportunity. Definition of immune checkpoint is not only related to T cells, but immune checkpoint are molecules which can control the activation, the strength of the activation of immune response. And we can find immune checkpoint at the level of progenitors, the level of mobilization. And I believe that we need to learn more in order to generate integrated therapeutic approach, which can improve the quality of our therapies. I finished. I thank only my groups and the collaborators, and thank you for your attention.
So Antonio, thank you very much Very interesting results. I mean, several different things to discuss and very important and interesting insight. So I have one first question from the audience. It's Patricia Zancan. Excellent presentation. Congratulations to Dr. Sica. One question is regarding NF-kappa B. Since it's classically associated with inflammation or M1 polarization, but you're showing that it is also associated with M2 polarization. Does it mean that NF-kappa B can coordinate repolarization of macrophages from M1 to M2 profile? I ask this because this repolarization process is often questioned. So what's your insight about it, Antonio?
Yes, no, the NF-kappa B is made up by 5 different members, actually. It's not only P65. We have P50, P65, CREL, REL-B, and REL-C. So 3 of these members have the so-called transactivation domain in the carboxyl terminus of the transcriptional factor. P50 and P52, sorry, they do not have the transactivation domains. The consequence is that if P50 or P52 form homodimer, they are not activating inflammation. They are actually inhibitor of inflammation because they recognize the same binding sites, but they do not own transactivation activities. And what we demonstrate is that in LPS tolerance, for example, but also in cancer-rate inflammation, the accumulation in the nuclei of tumor-associated macrophages is due to the P50 homodimer. So it's accumulation of an inhibitory NF-kappa B dimer, which is different. The relation, I mean, the ratio between the different heterodimer, homodimer, of course, is a controlling the final phenotypic functional phenotype of these cells in terms of anti-tumor, immunosuppressive, pro-tumor, anti-inflammatory, inflammatory, and so on.
Still on this issue, Antonio, regarding, because you showed lots of P50 knockout models and the contribution of those knockout cells, and I don't know if exactly repolarizing, but changing the profile of the macrophages from M1 to M2 and vice versa. So do you have good inhibitors for this selective unit of the NF-kappa B, the P50, and what would be, and this applies also for the CSF inhibitors, what would be the consequence of long-term inhibition of this kind of molecules, both CSF1 receptors and P50? So
there are not specific inhibitors of P50 and NF-kappa B for this subunit. I mean, some have, I mean, P50 is generated from a precursor, which is the P105, through a proteolytic process. It's the proteasome which generates P50. And people have tried to generate specific inhibitor, but they did not succeed, actually. However, we published that the P50 accumulation is controlled by tumor-derived signals, actually. And the one signal is IL-10, and another one which is more relevant to us is prostaglandin E2. Prostaglandin E2 is able to induce selective accumulation of P50 homodimer. Now, prostaglandin E2 is produced by several tumors, actually, and we inhibited the activation of P50 induction by using an antagonist of the AP2 receptor, which is one of the 4 receptors for prostaglandin E2. You can interfere with prostaglandin E2 activity, and you block accumulation of P50 and NF-kappa B. In this condition, we observed relevant anti-tumor effect, both in the fibrosarcoma and in melanoma. So you can play and try to attempt to block upstream signals that control P50 and NF-kappa B accumulation.
That would be your approach, to go upstream and try to.
Yeah, we did that, and we have there is a cancer research paper that we published last year, but I didn't talk, it was too much really. Blocking continuously P50 and NF-kappa B and MCSF Well, P50 and FKB has been related to autoimmunity. I mean, the silence of P50 and FKB, genetic defect for P50 is associated with autoimmunity, mainly driven by the dendritic cells. There is a quite old paper which discusses about, and this is quite reasonable because you are trying to exacerbate, you know, M1 Th1 immunity. So you can anti-MCSF receptor long treatment. No one has done this, but keep in mind that there are MCSF receptor knockout mice, which live quite well. The major problem with these mice is that they are osteoporotic because MCSF is in the trail pathways involved in the maturation of osteoclast and so on. So that's the point. So, but no one has done, of course, long treatment with these molecules. I think that now they are doing clinical trials and they will release some data about this issue, definitely.
Yeah, this osteoporotic aspect is concerning, right? Since it would be used in 5th to 6th decade women, so I don't know whether it's a good deal. I have a last one here, Antonio, a quick one, so we can, and then we'll have to finish because I'll do the schedule. So Claudia Lage from WFRJ is asking, she's commenting here that some 15 years ago, she saw a paper reporting the use of iron chelating agents as components of chemotherapy against iron accumulating tumors. Given the essentiality of iron in metabolic active tumors, these kinds of compounds, the question is whether these kind of compounds could be added to chemotherapeutic protocols for specific tumors. Considering your last part of this very nice set of...
This is a very, very good question. The point is that, let's put it this way. We need iron for several homeostatic physiological function. Supplying so much iron, you have to keep present that there is one pathological state, which is hemochromatosis, which is the accumulation of iron in different tissue. Scavenging the iron for blocking anti-tumor tumor promoting condition can be better to be selective in the tumor lesion. To block, I mean, iron specifically in the host will interfere definitely with the oxygen delivery, which are our capacity to feed the erythropoiesis, because we need erythropoiesis, of course. So you are interfering with a very, very key physiology. That's the point. I don't know, but of course it is something that is worthy to be studied. Yeah, definitely.
Sure. So Antonio, thank you very much once again. It was a pleasure to have you here. Hopefully we can arrange to see each other, to bring you here in person next time. So and congratulations for the work. It was very nice to see Chiara's work and other people, Alessandra's work, other people's work from that time. Very nice stories, and congratulations